principle of surface machining. What does it mean? On surface, again, I have the silicon oxide and I build on it. Historically, bulk silicon machining was first, I should say, discovered. It's not discovered, it was basically discovered by accident. What happens? Silicon, you might know these wafers are made from single crystal. So that means what? The material is organized such in a way that all the atoms are at the right place. There is no vacancy, there is no defect in the structure. It's a perfect monocrystalline structure. Now, in this monocrystalline structure, the atoms of silicon are arranged in a structure diamond-like. That means we have atoms in each point, cubic face, and inside is not center, but I have a diamond structure. Eight more atoms position, such that the distance among all the atoms is same. So this is the perfect diamond structure and silicon structure as well. Now, in this silicon structure, you probably recall about Miller index and the crystallographic planes. It rings a bell. What 000 or 010 means. It goes with the crystallographic plane. I don't know if I have here now that I have in the lecture. So if you take x, y, and z directions and the atoms in the cube there, 1, 1, 1 would be a plane that cuts all one position, be diagonal through. Now, if you go through this structure and you count the atoms, maximum number of atoms will be on 1, 1, 1. It will be 8 atoms in the cube. The point is that there are certain chemicals, hydroxides mostly, they remove silicon selectively. We call anisotropic etching because the etching goes with different speeds in different directions. And this speed is not 1.5 times, it's 400 times higher. So 111 etches the slowest, 100 etches the fastest. So according to the orientation of the wafer, on a wafer that is oriented 100 is cut on the crystal that gives me, orientation 100. I could get trenches inclined at 54.74 is the angle of this planes. Absolutely perfect. This surface is mirror-like. It's absolutely mirror. So one could build these things. The first sensor, as a matter of fact, ever built and commercially shown sold basically, was a bulk machining, was a microaccelerometer, and that company now belongs to Lucas Aerospace. It was, changed hands a lot. One could go to have through holes, and by the way, these through holes, they make the core technology for the inkjet printing heads. And they make all the inkjet printing heads, they are made in this silicon technology. Wafer is thinner, but the nozzle is lighter, and all the droplets of ink that come out, they come out through that nozzle, a convergent divergent nozzle. So silicon insulator is absolutely the same. I don't know if I have a picture in here. No, I don't have. But imagine that I have oxide, and on the top I have silicon. I can't etch bulk on that material. I just can build on the top. And eventually the active components, they could be embedded. Active components are always in the silicon. They're only one layer. All transistors and diodes, they will be within silicon, they are buried, and it's only one layer. I don't have multiple layers on that. And on the top I have resistors and capacitors. And circuits, of course. So that is the idea. Now, one could use this silicon insulator, have silicon on the top. Either you can bond another silicon on the top, a thick silicon, and have silicon oxide, silicon, two thick silicon and one oxide thing, and play with that. Like a bulk, see? Or the work could go only on the electronics that will be built on the thin oxide silicon on the top. Oxide and silicon will be the structural layers, membranes, measurement devices, beams, and so on and so forth. So there will be the same fabrication steps, no doubt, in this technology. If we talk about the electronics, if we talk about MEMS, we have the same additional process on the top of the silicon if we want to do that, or a subtraction of silicon from the wafer, basically. This will be in the bulk of silicon, and here we have silicon oxide, and on the top silicon. Silicon could be used for circuits, piezoresistors, contacts, and so on and so forth. And the silicon oxide will be the sensing element. So that is a valuable structure. It's used in many pressure sensors. It's like that. These are a few examples. It's a coil, it's an inductor, but it was used with success as a light bulb filament as well. So just for the illustration, these are cantilever beams used for detection of the laminary layer. So what happens through the flow, these cantilever beams, they are very sensitive. They will go down. Sure, it's extremely important they are not touched by hand because the force induced by hand, it's not controlled. But the flow will just put them down. Now, if there will be a separation of air, it will be turbulence, these beams will start shaking, and eventually the shaking could be detected. So they are good candidates for that type of technology. They could be built in silicon. This is silicon on insulator. So they could phase easily to 150 degrees even with the electronics attached. So again,
is the coil also silicon?
This is the silicon coil. Right?
And you can burn.
You could heat it up. Yeah, it doesn't last long, but if it's no oxygen, it will last for good time. But it's a coil in general. What happens in electronic circuits? There is no inductance. You can't build inductance. Inductance is always outside. So that is an interesting point. In radio frequency, you need inductance. You need capacitance inductance just to treat the circuit. So that would be this is one of the things MEMS guys they brag they can do radio frequency devices. Trained very well. So electronic circuits built on the top, again, they could operate up to 300 degrees. 250 safe, up to 300. Silicon carbide technologies. They are based on the same CMOS. CMOS is complementary metal oxide semiconductor. This is the acronym of the CMOS. The same silicon carbide, I use the same technology. That means I could build transistors, I could build diodes, and then on the top, capacitors and resistors. Absolutely the same thing. The issue is that the temperature for which the electronics operate is 500 degrees. The issue is not now, you probably will laugh a bit. The issue is not circuiting here anymore. The issue is the pads, the contacts they will take to the circuit outside. Metal on silicon carbide will diffuse at 450 degrees. Before, the other impurities will diffuse in silicon carbide. That is a serious drawback. What they use aluminum normally, gold, and copper. And all of them diffuse at 450 degrees. The life of such a circuit is no more than 50 hours at this stage, at temperature exceeding 450 degrees. Now, I'm sure if you're in aerospace business, you know very well that there are companies providing sensors for testing purposes mostly, and Carbide is one of them. They are a very successful company because they have small production, only on demand, and they control very well what they do. They have very good products indeed. But again, very expensive. They are not intended to fly. They intended just for the testing, right? So there will be other companies that I have just included here that they could do silicon carbide technologies. I think NASA probably is the most advanced, has the most advanced facility on silicon carbide. Case Western University, University of Berlin and DEF, they have very good facility. In Japan, they have good facility, but they're not NATO. And this other companies, they are small emerging companies. If one wants to watch them, what they do, that would be a good point to do that. So how silicon carbide looks like. This is a picture from the, you see, NASA sensor, but Carbide is making the silicon carbide in NASA, right, in their facility. So overall, what happens in this technology is it's like silicon on insulator. On the top of the silicon, they put a layer of silicon carbide, and they etch silicon, and they let silicon carbide on the top. On this silicon carbide, they have the strain gauges. Strain gauges located in specific locations where the stress would be, or the strain would be maximum, right? And with that, they could measure temperature at very high pressure at very high temperature. Metallizations are the weakest point in here, as I have mentioned, because of that. Electronic circuit is built on the side. Here is the membrane side. Wires, they would lead to the electronic circuit is down. Electronic circuit. Usually what the electronic circuit includes basically a converter from the resistance to current, eventually digital to analog to digital, and we have a digital output. Now issues would be how one with silicon carbide. That is one of the issues. Silicon carbide requires a special type of technology to be etched. It's not etched like silicon. Silicon could be etched either wet in liquid, in chemical liquid state, or gases. And gases are the most accurate etching, but definitely they are environmental, not too friendly, and quite expensive. Now, about the packaging of silicon carbide, this is a good example of bonding, fusion of the chip with the glass would enable good properties. Circuit basically, as is right now, as is shown in here, would invert the membrane. The membrane is the other side. I mean, this will go side up, as we can see here. The electronics would be somehow sealed, not to be exposed to the conditions. And contacts are made outside. Now, why contacts through this bonding? Because soldering works up to 100 degrees, right? Talk about 450 degrees. You have to make sure you have a strong contact. And this is not mundane. This is a serious issue. Now, if we talk about 500 degrees wires from here, they are not standard wires, right? They have to have another insulator. They have to have other properties. I know wires are available. Everybody will tell me we have wires that operate at 750 degrees, 800 degrees. Yeah, but what is the weight? What is the cost? If we want to make a business case, one has to look into that as well.